there's a particle acted on by an outside force and travels along the curve, r of t. And r of t, it's this vector valued function. We know it's a vector valued function because there's these nice sharp brackets on the ends. And the x-coordinate behaves like minus 3 e to the minus 2t minus t minus 4. The y-coordinate 4 cosine t plus sine t. The z-coordinate is arctangent 2t minus 6. At time t equals 0, the outside force, it stops. And so the particle continues moving along its tangent line because a particle in motion tends to stay in motion. It's almost like a law. And so it says, well, how does it move? Well, it just says, how am I currently moving? Okay, I'll keep doing that. And the tangent line is telling it how it's currently moving. So the question is, at what point will the particle hit the xy plane? And there are some options. Negative 740, negative 250, 360, 870, 1380. You might notice that all these options have something in common. What do they all have in common? They all have zeros on the end. Coincidence? No, it's not a coincidence, because when you hit the xy plane, what's true about the z-coordinate? It's 0, right? And on a side note, I finally got to see the draft of the multiple choice problems. And we need to work on some of those problems because they're too easy to eliminate answers. We have to make it more interesting. So I want you to get the full experience. So well, we'll see what happens. They'll probably say, don't worry about it. Don't worry about it. But you would notice, for instance, if one of these had a 2 in the z-coordinate, you'd be like, it's not that one. So one of the things that you probably have learned a long time ago, but just in case, it's oftentimes just as useful to eliminate things as it is to figure out what the actual answer is. Okay, you've had a few minutes. And there's not a big rush today, I don't think. Do you need a few more minutes, or are we ready? Yes, we need a few more minutes, or yes, we're ready? Yes, we're ready. Okay, all right. Then in that case, do we have an answer? Someone said A. Someone said D. I don't know if I heard any B, C's, or E's, though. Now, A is very tempting, right? Because where would you get these numbers negative 7 and 4? Well, if you just plugged in 0 into R, you get negative 7 and 4 here. And that's if your particle is sort of moving through space and then it stops and goes, whoop, just drops straight down. But particles don't tend to drop straight down. What do? They go on a straight line, right? Now, it could be that the particle might drop straight down, but probably not. Probably not. So the answer is D, 870. So negative 7, 4, negative 6, that is where the particle is at time 0. And you say, okay, great. That's when the force stops. Take the derivative at time 0, and you get 5, 1, 2. So the tangent line in vector form, your point plus some multiple, I'm using S here, just to remind myself that this time parameter is not the same as this time parameter. In some sense, there's a resetting of time. So the line behaves like negative 7, 4, negative 6 plus some multiple of 5, 1, 2. And we can write that in parametric form. And so we know where x, y, and z is for any choice. And we say, well, we need to hit the xy plane. That means z equals 0. That tells us that our choice for s has to be 3. And that gives us our x and y coordinates. So now we know where we hit the plane. So it used to be on, we used to do a problem on the quiz where you were holding an egg and you dropped the egg and it would splat on the xy plane. But they took that problem off. All right. I don't know. Probably people were like, this is too anti-egg or something. That's my guess. All right. So, today's thought. Well, No surprise. We've been building up to this. We've been talking about problem solving. So, step 4. And if you remember our first 3 steps, let's see if we can remember them. Step 1, understand. You can't solve a problem if you don't understand it. Step 2, make a plan. And this one is going to tie into step 4 as well. So make a plan. And the easiest way to make a plan is to say, I wonder if I've seen something like this before. Let me try the same thing. Step 3, kind of solve it, right? Carry out the plan. You're like, well, wait, hold on. Shouldn't we be done? Shouldn't this be only 3 steps? So what's step 4? This last step is to say, look back at what you did. So you look at the problems and you say, well, what did you do? Why did you do it? And would you be able to solve something similar in the future? So you want to take some time and prepare for that future step 2. So the goal of solving a problem is not to say, I need to solve this one problem and then I'll never think of this again in my life. The goal is to say, I'm going to solve this problem and all future problems like this. I'm going to figure out why I did what I did, what mistakes I fell into so that I won't make those same mistakes, and I'll learn to recognize, to set myself up. So taking some time and thinking about why you do things goes a great, tremendous way to helping you solve problems in the future. So always think about, what did you do? Why did you do it? So that you can be ready to solve those problems in the future. All right, so that's our last step. Now we know how to solve all the problems. Well, in theory. Okay, so what's today? So our goal for today is not too bad. We're going to be talking about motion. And so we have position. We said we're going to use our vector valued functions, r of t, which we can write as in component form, the x component, y component, z component, and that can keep track of our position. Now, of course, remember that r of t is a vector valued function. It's not the same as position quite, but we're going to treat it like it were position. Why do we use vector valued functions? So we can calculus with it. All right. So we start thinking about things we like to do. We put on our physics hat, if you will. We say, okay, well, what are things that we'd like to do? Well, we'd like to understand how position changes. And as soon as you start talking about how things change, that means derivative. So if I want to know how position changes, I take the derivative of position, and that's our r prime of t. And of course, the punchline is that when I want to take the derivative of a vector valued function, I work with it entry by entry. So that means the derivative of the first entry, derivative of the second entry, derivative of the third entry. All right, so that's how position changes. That has a name. We call that velocity. So velocity is the change in position. Now there's a note here that says there's another idea called speed. And speed and velocity are related, but they're not the same. And in particular here, you'll see speed is the magnitude of your velocity. So sort of, in essence, what's the difference between speed and velocity? What separates them? Velocity has direction. And that's what it boils down to. So velocity has additional information. There's a direction built into it. And this is true, by the way, of even just single variable calculus. You might say, what are you talking about direction? We didn't have direction. Yeah, you did. You had this thing called plus and minus, where plus, you were moving in the positive direction, and minus, you were moving in the negative direction. So those signs were about orientation. They were about direction. So we say, okay, great. So we have velocity, we have speed. We're going to talk a lot more about speed in our next lecture. So good, fun things to look forward to. When I say, okay, well, I can say that velocity is how position changes. Can I ask how velocity changes? Yes. And how do you do that? Well, you take another derivative. So the second derivative, r double prime of t, which is x double prime of t, y double prime, z double prime of t. And I didn't write this down, but I should have, but that's okay, I can write it down now. This is the same as just v prime of t. So this is how velocity changes. And that's what we call acceleration. All right, so acceleration, change in velocity. Now you could say, could I go further? Yes. Are we going to? Well, not in terms of motion. This is as far as we go. All right, so we have position, velocity, and acceleration, and they're nicely connected to each other. And we've already seen some ideas. We've seen, for instance, that you can combine this notion of position and velocity. So if you add those together, you can form the tangent line. And okay, so that's the r of some initial time plus t r prime of some initial time. Okay, so we can do that. But you might say, can we go further? Can we go further? And all right, well, yeah, sure, we can do that. Here we go. We can actually combine all three ideas. We can combine position plus velocity plus acceleration. And we have to think about how are we going to do it. So let me try to explain it. So imagine that you have a curve. So here's a curve traveling through three-dimensional space. And we say, all right, great. And well, if we have this curve, we can talk about its position, that's the point. We can talk about our velocity, which would be in the direction of motion, and then we have acceleration. Now, it's not so clear exactly where acceleration might be. It might be in the direction of motion, might be off to the side, might even be exactly opposite, but it's in some direction, so there's acceleration. So we start thinking, okay, all right, what kind of object can we use that can encapsulate a point and two directions? Is there an object that we can do for that? What? A plane! Yes! Yes! Okay, so this leads us to what's called an osculating plane. All right. So here's this osculating plane. Now, does anybody know what osculate means? You perhaps heard it wandering around campus. Perhaps someone has said, hey, do you want to come over to my place later and maybe we can osculate for a while? You don't know what that means. Maybe it's very clean. I'd say. So osculate means to kiss. That's its one version. So it's like a kissing. Whoa. All right. Okay. Don't report me. So anyways, so osculating means to kiss, and so it's the kissing plane. All right. So what's the idea? So the osculating plane incorporates the position, the velocity, and the acceleration. So how would we actually go about finding the osculating plane? Well, when you need a plane, what do you need? You need a point. So what's our point? Yeah, our position, our t0. And then we have the normal. So whenever you're after a plane, you're always like, I need my point and I need my normal vector. How do we get the normal? Cross product, because we have two vectors that have to be in our plane. We've got that velocity vector, we've got that acceleration vector. So if we have two vectors that are in the plane, the cross product will give us a vector that's perpendicular to both. In particular, that's the normal to the plane. So this is our prime of t0 cross our double prime of t0. This cross product makes normals. All right, good, good. Well, let's try an example, shall we? Any questions before we move to our example? We did tangent lines, so our new thing is osculating planes. Okay. All right. Find the osculating plane for, oh, it's a blank. That means we get to make up a problem. Okay. Now, before I open the floor to suggestions, to be clear, when I say make up a problem, you're going to do this problem. So keep that in mind as you make suggestions. And it can't be too easy, right? Just the right amount. So, of course, we have to have a curve. For the curve, r of t equals. So what will be the x-coordinate? Sorry, what? Tangent of t. Interesting. Tangent of t. Should we throw a number in front of it? 4 tangent of t. Maybe we should throw one more thing in here so it's not so lonely. How about a 2? 4 tangent t plus 2. Okay, now we go to the y-coordinate.
E to the 2t plus 3x squared.
Okay, so interesting combinations of things. Definitely e to the 2t I'm cool with. And the 3x squared, I think you meant to say 3t squared, because they should be functions of t. No worries, no worries. You know, we gotta get into that mindset. Everything depends on t. All right, I can see that. It could work. Cool. All right, one more slot. 6, 0. Come on, come on. Live a little. Spice it up. Do you really want to take the second derivative of arctan? No. No, I wouldn't mind. But I'm not the average person. Okay. So, ln of, you really want to go there? Okay, my goodness. I have some great students, enthusiastic students. Okay, we can go ln of something. 1 plus t. Don't worry, you'll survive. You'll survive. We'll add a 4t and a minus a 2. How about that? Okay, there we go. So here's the question. Find the osculating plane for the curve r of t equals all this. Now there is one more thing I have to write down because this question isn't complete. What's the last thing? The time. Well, I suspect we'll go with time equals 0. Because we love our students. Let's compare. Is anyone really confident says, I think I have an answer? I see a hand. Okay.
I don't have it in the correct format, but I have a point and I have a vector.
What's your point?
I had 2, 1, negative 2.
I agree with that.
And my vector was negative 52, 4, 40.
I also agree with that. Okay. Phew. All right, success. Now you'll notice I made a mistake here and I had to correct myself. So yes, we make mistakes, but we say, wait, that doesn't seem right, and we fix it. So some good news, log of 1 is 0, tangent of 0 is 0, e to the 0 is 1. So we get nice numbers. Oh, and by the way, 0 is also 0. And so the point is 2, 1, negative 2. The first derivative of tangent secant squared, 2 comes down in the e to the 2t. derivative of natural log is 1 over, which you can think of as t plus 1 to the minus 1 power. And then there's the plus 4. And so that says that the derivative at 0, which is what we need, is 425. Now, the derivative of 4 secant squared is 8 secant squared times tangent, which doesn't quite seem right when you say it out loud. But what you do is, it's a chain rule. The 2 comes down, so that's where the 8 comes from, times secant. Then what's the derivative of secant? Secant tangent. So that's where you get 2 secants from this secant and then from the chain rule secant tangent. And it looks terrible, but the tangent of 0 is 0, which knocks out that first term completely. The second term will be 4e to the 2t plus 6. The third term will be minus t plus 1 to the power minus 2. So the acceleration vector is 0, 10, negative 1. We have our point. We have our 2 directions. We take their cross product. We get big numbers, but I encourage you to say, oh, look at these big numbers. Is there anything in common? They're all multiples of 4. So you can pull out the 4. Because normal vectors aren't unique. It's not the normal vector. It's a normal vector. So work with a convenient normal vector. So instead of working with negative 52, 440, work with negative 13, 1, 10. That's the same vector, just scaled. So these are your coefficients. Minus 13x plus y plus 10z equals something. You plug in your point to get the something. And so we have the answer. I don't like negatives at the front, so that's why I flipped the sign. But other than that, life is good. Wonderful. We can do these questions if they were on an exam. Will it be on the exam? I can't remember. I don't know. I have a bad memory. But it has been on exams in the past. Any questions? Yes?
Why is it that when we plug in a point into the solution vector, we are getting a point and not a vector?
Great question. So why is it that we are thinking of, when we plug in a time 0 into this r of t, it looks a suspiciously lot like a vector, and why are we calling it a point? So this goes back to our discussion last time, which is to say, well, we could call r of t, we could give it, in terms of a point, put parentheses instead of these vector brackets. But the issue is, you can't do calculus with that kind of function. So what we're doing is, when we think of r of t, we are going to think of it as a vector, but we're going to nail the end of the vector to the origin. So r of t is the vector that points to our current location. And so we're thinking of this, even though it's a vector 2, 1, negative 2, we're thinking of it as it's the vector that starts from the origin and points to our current point. So we say, aha, that means we are currently at the point 2, 1, negative 2. By thinking of it as a vector, we're allowed to do addition and scaling, which means we can do the calculus. So that's why we do it. The convention, I guess. Okay, yes?
Why can't we use the position vector and velocity vector to find the normal vector? Why do you need the acceleration vector to find the normal vector?
Well, because, okay, great questions. It's because what we're interested in is the plane we want to have contain information about motion. And whereas the position vector, it doesn't really contain information about motion, it contains information about location. So this position vector is storing, it's a location information, not a movement information. So we want to use the r prime and r double prime because that's movement information. That's how it's changing. So that's the conventions. Anything else?
If you don't pull out that 4, say if this was like on the exam, that'd still be an acceptable answer.
Yeah, you could put 52x minus 4y minus 40z equals 180. Same plane. Same plane gets you same points. Because writing the way you write a plane is not unique.
Where does the negative 45 come from?
The negative 45, yeah, so negative 45, these numbers here gave us our coefficients, but in the plane there's this other number over here. So what happens is you plug in your point. So it's really negative 13 times x plus y, which is 1, plus 10 times z, which is negative 2. So you get negative 26 plus 1 minus 20, and you add those up. So that's the negative 45. So it's essentially saying, I'm almost there. I've got like most of my plane. I just have this little box. And it's the age-old question, what's in the box? What's in the box? And the answer is you plug in your point. And that fills up the box. And there you go. All right, great, good. We're learning all sorts of things. All right, now, any last questions? Okay. Well, I appreciate you asking questions. All right, so we've talked about, you give us position, we can find velocity. We take derivatives. But what if we have the opposite issue? What if we have velocity, or maybe we have acceleration, can we find position? And the answer is yes. Because we say, look, you give me acceleration, you've really given me the second derivative. And so how do we get from the second derivative to the function? You use integration. You use antiderivatives. And so we can just integrate. And now you might say, okay, but how do we integrate? Well, we integrate term by term, entry by entry. And like, whoa. Isn't that how we do derivatives? Yes, exactly. Entry by entry. Because if you think about it, like if I should have pointed this out. We are essentially doing a lot of Calc 1 problems here. But now, normally in Calc 1, you would have just had like either that, and say what's the second derivative, or this, and say what's the second derivative, or this, and say what's the second derivative. So what we did is we said, oh, let's give you 3 little Calc 1 problems. So it's like Calc 1, you just get to do it 3 times. So, same thing with integration. It's like Calc 1, you just get to do it 3 times. And so work entry by entry. And you can also do definite integrals, not just antiderivatives, work entry by entry. So let's see. In the interest of time, let's suppose we make up a very simple thing. Now, when you're making up a problem for saying, here's position, find acceleration, you just take anything anybody throws at you. When you say, here's acceleration, find position, you're like, I'll write it down what I want. Because it turns out it's harder to integrate than it is to differentiate. I don't know if you've ever noticed that. But I have. All right, so let's suppose you have 6t plus 4, 9e to the 3t, and 4 sine t. So there's acceleration. And we have some initial information. So let's suppose we know that at time 0 our velocity is 215. And at time 0 our position, which, whoops, not s. That's my other lecture. R of 0 is given by 1, 0, minus 2. And now I say, well, what's r of t? Okay, so what do? We just work our way up, one level at a time. And so we integrate. So first thing is we go from acceleration to velocity, one layer. So if I want velocity, that's the antiderivative of acceleration. So I say, okay, let's work term by term. What's the integral of 6t plus 4? 3t squared. Plus 4t, plus a constant. So you get a constant in each slot. Each entry gets its own constant. Ooh. What's the integral of 9e to the 3t? 3e to the 3t plus, well, we've already used c. Get to work our way through the alphabet. And now the integral of sine t, well, 4 sine t, let's not forget that 4. Oh, you guys are good with your signs. Yep, the integral of sine is negative cosine. You got to keep track. Plus, well, we can use e with a capital letter. But you can use f. That's okay. We'll get to use more constants soon. Don't worry. All right. Now, what should be our next step? Yeah. We can use our information about v of 0 to solve for our constants. We could go ahead and integrate now and solve for constants later, but I like to solve for constants as soon as possible, but not sooner. So, 215 is equal to, we plug in times 0. That's our v of 0. So, 3 times 0 squared plus 4 times 0 plus c. That's c. 3e to the 0 plus d. Yep, d plus 3 or 3 plus d. Minus 4 cosine t plus e becomes minus 4 plus e, because cosine of 0 is 1. What is c? 2, right? Because we just match coefficients. C is 2. How about d? Minus 2. How about e? Sorry, what? 9. Cool. Cool. So c is 2, d is minus 2, e is 9. All right. So now we can do our update. So we have our velocity is 3t squared plus 4t plus 2. 3e to the 3t minus 2. Negative 4 cosine t plus 9. All right, now we integrate. What's the integral of 3t squared plus 4t plus 2? 3.5 t to the third? It could be 3/3 t to the third. How about just t to the third? Does that sound reasonable? Plus 2t squared, okay. Plus 2t plus? Well, we already used c. That's f. If you think this is bad, wait till differential equations. We get up to like r and s sometimes. But usually we don't ask you to solve. But you have to write it down. Oh, it's good times. Okay. Integral 3e to 3t minus 2. E to 3t minus 2t plus? U. Well, we should probably go in order. We'll go with g. Integral of negative 4 cosine t plus 9? Negative 4 sine t plus 9t plus h. Okay, are we done? No, we're not done. What do we need to do? We need to plug in, right, our initial conditions. So 1, 0, negative 2, which is your r of 0. 0, 0, 0, f. That has a familiar ring to it. I don't know why. All right. 1 minus 0 plus g. That's 1 plus g. 0, 0, h. Okay, so we get that 1 has to match up with f. So what does that tell us? F is 1. 0 has to match 1 plus g. Negative 1. Negative 2 has to match with h. So h is negative 2. So plug it in and we get our final answer. So we get t cubed plus 2t squared plus 2t plus 1, comma, and then we get e to the 3t minus 2t minus 1, comma, negative 4 sine t plus 9t minus 2. So it really is Calc 1 type problems. You just have to do it one slot at a time. Okay, all right. So I want to ask a couple of questions here. We'll test your geometrical intuition. So we know how to integrate. Suppose we're in three-dimensional space. That's not so hard to suppose. Some of my best friends live in three-dimensional space. So we have our curve doing all sorts of curvy things. And we are going at time t equals a, we're at some point, and at time t equals b, we're at some other point. And now I want to ask about integrals. I want to ask about three integrals, and I want to say, what do these three integrals measure? Suppose I ask, I want the integral from a to b, r prime of t dt. Or I want to ask the integral from a to b, r prime of t dt, but take the magnitude. Or I want to ask integral from a to b, the magnitude of r prime of t dt. Are these the same? Are these different? And if they are different, what are they measuring that's different? Now, I probably have, there's a clue here. This feels very familiar. Probably like fundamental, even. Do you think you could solve this? If you could solve it, what would it be? Right, it's like r of t from a to b, which is the vector r of b minus r of a. What does that vector look like? When I take a subtraction of vectors, what am I really doing in terms of this picture? So in some sense, you know, r of a is that vector, r of b is that vector. What's the subtraction doing? You're doing what? Projecting. It's not quite projecting. What would you like it to do? You'd like it to be this. And it is that. It's the vector that goes from where you are at time A to where you are at time B. So it's the vector connecting. Now, in physics, I think they probably call this displacement. What was this doing? So you're finding the magnitude of your displacement. So what is this measuring? This is the distance between the 2 points, between the point r of a and r of b. Like, how far apart are those points? So what's this then? The integral from a to b of the magnitude of r prime of t dt. Come back next time, and we'll tell you the story. Actually, no. We have a minute. We have a couple minutes. Do we have a couple minutes? No, we don't have any time. Okay, but you come back next time, we will talk about this. And I would normally say, and here's a fun problem. What could it be? What could it be? A, B, C, D, or any guesses? A? Haha, it was actually C. Oh well, all right. Thank you for coming. See you next time.